Good evening, everyone. Welcome to the fourth problems week problem for the problem solving session related to structural analysis course. So this is your fourth problem solving session. So in this, we will try to solve the problems related to topics what you have covered in this current week. Let me share my screen first. Then I will show you the topics whatever you are covered, and we will solve the problems related to that topic. Okay. I hope the screen is visible to everyone. So let's start the session. So this is your fourth week related to structural analysis course. So till now, what we have covered, we started with analysis of beams for shear force as well as the bending moment calculations. Then we solved the problems related to statically determinate structures, in which we have seen the problems related to trusses, that how to solve the members forces, how to calculate the member forces in trusses using method of joint as well as the method of section. Then we've determined the deflection in truss members using unit load method, which is based upon principle of virtual work. So what does principle of virtual work tell you? It tells you the total work done by a system is equal to 0 when no external force is applied over it. Okay, so this is what we have covered till the previous week. So this week we started with beams and frames, and we have seen how to solve the problems related to beams and frames using moment area method. So in this session, we will solve the problems related to beams and frames, and we will find the deflections and slopes in them using moment area method. Okay, so your week 4 included calculation of beams and frames using moment area method. So what is the difference between a beam as well as truss? Why we are not solving the problem using principle of virtual work? This is because truss member is a two force member in which no bending moment is coming into the member structure. Whereas in beams and frames, every member will have axial force or shear force as well as the bending moment in the structure. So to incorporate that, we will utilize moment area method. So what does moment area method tells you? So first of all, there are two theorems which defines the moment area method. So first theorem says that the change in slope between two tangents drawn to the elastic curve at any points between A and B is equal to the bending area, bending moment diagram between A and B divided by EI. So that means you have, so what does this theorem tells you? It tells you, suppose you have a beam. Let me draw one beam. So suppose this is your simply supported beam having hinge at one end and roller support at the other. So in this case, if you have uniformly distributed load like this, if you have uniformly distributed load over the section, so in this case, the change in slope, to mark some points, the change in slope between the tangents drawn to the elastic curve at any points between A and B. Suppose this is your point A and B. So that means the change in slope. So suppose this beam undergoes deflection like this, and the slope angle in this is theta A, and in this it is theta B. Okay, so your change in slope, that means theta A minus theta B between the two tangents. So that means suppose this is your tangent So this is your first tangent and this is your second tangent. Okay, let me write theta A and theta B again. So that means theta A minus theta B will be equal to area of bending moment diagram between A and B divided by the modulus of elasticity of the section. That means EI. Fine. This is the first theorem of moment area method. So in what purpose we will utilize? So we will utilize to determine the slope of the beam that is provided to you. So whenever you have to determine the slope of a section, what you will do? You will take the area of the bending moment diagram between A and B, and then you will divide it by EI. It will give you the slope at that particular point. Okay, so how it came? So suppose you have a beam, simply supported beam, having hinge at one end and roller support at the other end. Okay, so how it will deflect? So this is the deflection profile of this beam under any load. Okay, so if this is the deflection profile, if you see in this case, you have theta A and theta B come into picture. So this is the slope of the deflection profile. So this is your theta A and this will be your theta B. Fine. So suppose if you are taking this as positive x and this as positive y. Okay, and you mark any section HH. So if this is your H section, okay, then how you will define slope? Okay, so slope will be defined by the change in the rate of change of displacement will give you slope. Okay, now you already know from Euler-Bernoulli equation. So from Euler-Bernoulli's equation, d2y upon dx square is equal to minus m over ei. You know how it came? Now, if I take 1 d by dx out, okay, what will come inside? dy by dx. That will also be equal to minus m over ei. So this will give you rate of change of theta. So now I can write dy by dx equal to theta. So then your d theta by dx will be equal to minus m up over ei. And since ei is constant and m is a function of x, so I can write m to be equal to phi x. Okay, so this is a function which is dependent upon x. Okay, now if I made the projections of this beam like this, so suppose this beam is deflected into this shape. Okay, let me take the next page. So if I again draw the deflection profile of this beam, suppose this is your beam and it is deflected like this, and in this case if you draw the tangents, Okay, so this is your first tangent from A, or you can say the slope line of A, and this is your slope line from B. So that means this is your theta A, and this will be your theta B, and this angle will be theta AB. That means the change of slope with respect to B. So another thing you can find out, if you draw the projection of deflection obtained on the slope line B, so how can you define it? So this is deflection at point A on the slope line of B. Similarly, we can do for this. So for B also, we can write this is projection of B on the slope line of A. Fine. Now let me remove the additional parts. Okay. So from this diagram, you can write that delta BA is the projection of point B on the slope of A. So from this, how what we have calculated earlier, from earlier derivation, we have determined that del theta by del x is a function of some function phi, which is dependent upon x. If we integrate them, so what you will get? So you will get, if we integrate from A to B, you will get theta into dx. That will be equal to minus from A to B phi of x into dx. Fine. So this you can write as delta B minus delta A. That will be equal to minus integration of phi x with respect to dx. Okay, so from this you can see that the change in slope is equal to the area of the bending moment diagram that is covered by phi h. Okay, so from this we have proved the first theorem of moment area method. Now let's talk about the second theorem. So now we can also say that d delta BA is also equal to xb into d theta. This is your simple triangular rule. Okay, so this will give you delta BA to be equal to integration of b to a xb into d theta, and from this you can write delta BA to be equal to integration of b to a xb. And how you can write del theta? Del theta, you can write it as phi x into dx. So this will give you the second theorem of moment area method. So what is the second area of the second theorem of the moment area method? It tells you that the deviation of point B relative to the tangent drawn on the elastic curve at any other point A. Okay, that means delta BA in the direction perpendicular to the original position of the beam is equal to the moment with respect to B. Let me highlight it with other. So it will be equal to moment with respect to B of the area of the bending moment diagram between A and B. That means moment B between A and B divided by area. Okay, so what it tells you that theta BA will be equal to moment of B divided by area into HB. Fine. So this is your second theorem of moment area method. So in simplest terms, if I tell you that how you will determine slope and deflection at a point, so you will determine using moment area method. Then how you will use that? So first, if any beam is given to you, you first determine its bending moment diagram. So after determining the bending moment diagram, if you have to determine the slope at one point, what you will do, from that particular point to the first point, you will determine the area what is covered under that section, and if you divide it by EI, you will get the slope at that particular point. And when you have to determine the deflection of that particular point, what you will do, you will take the area moment of that area between that sections A and B, and then divided it by EI. Okay. So this point you have to understand that what is the difference between first theorem and second theorem. So second theorem is for deflection, first theorem is for slope. In first theorem, we will take area of the bending moment diagram divided by EI. In second theorem, we will take moment of the area. So you will see this, that moment of area of the bending moment diagram between A and B, and then if you divided it by EI, it will give you the deflection at that particular point. So this is what you have covered in this current week. So we will solve some problem related to this topic. So if I tell you, if you already have seen all the videos of the current week, so many questions are solved related to finding out the slope and deflection at that particular point. And for the solving the easiest questions, or not to make every questions to be very difficult, what you will do, you will understand the basics related to slope and deflection for the simplest problems. So these simplest problems you can take note, and then wherever it is required, you can directly use these results. And if you want to solve the problems also, you can take a simplest problem and then see whether the results that are provided in this table, you are getting it or not. Okay, so these are the some predefined results that you can directly use in solving the problems, or if you want, for every questions you can solve also, and then it will some problems would become difficult for you also. So first question is, first term is, when you have a cantilever beam having a concentrated load at one end, so in that case, your deflection at point B, or I will write it here. So suppose this is your point A and this is your point B. So your deflection at point B will come out as PL cube upon 3EI. Fine. So how it will deflect? So this beam will deflect like this, and it will have the maximum deflection at point B, and that will be equal to PL cube upon 3EI. If you have to find the slope, so your slope is PL square upon 2EI. When you have a cantilever beam subjected to a anti-clockwise moment at the free end, in that case, your deflection come out to be ML square upon 2EI, and your theta also will be ML upon EI. So in this case, beam will deflect like this. Fine. Now next is, when you have a cantilever beam subjected to uniformly distributed load throughout the length of the beam. So in this case, beam will deflect like this, and you have the maximum deflection coming out to be WL4 upon 8EI, and your theta slope maximum that will come out will be equal to minus WL cube upon 6EI. One more case is there when you have a simply supported beam subjected to a concentrated load at the middle of the beam. So in this case, how the beam will deflect. So this is how the deflection of beam will look like. So in this case, the maximum deflection will come at the center, and it will be equal to minus PL cube upon 48 EI, and your theta maximum will come out to be PL square upon 16 EI. So these are some standard problems that are available to you. For those cases, you can you can take a note of all the standard results available for the standard problems. And for the rest of the cases, suppose you have a point load which is at a distance of A from point A, and from B at a distance B from the point B, then how you will solve? You have these results also. But basic 1, 2, 3, 4. So 4 cases, you can take a note of it, and 1 this also. So 5 cases, you have to take a note of them, and whenever it is required, you can use the results directly to solve any problem. Okay, so let's start some problems related to what we have covered regarding moment area method. So first question is, for what structures moment area method can be applied? So this is the basic question. So moment area method is, so let me write that moment area method is suitable for first, single span beams. Second, continuous beams. And third, it is frames. Okay, so for these structures, you can utilize the moment area method to determine the slope and deflection at any point of the beam as well as the frame section. So let's start to solve the problems. So what this question tells you, so this is the question number 2. In this, it is mentioned that in case of a simply supported beam AB, theta AP is the slope at A when a concentrated load is applied at the midpoint. So let's draw the diagram first. So we will first draw a simply supported beam AB having a hinge at end A and a roller support at end B. So now we have made a simply supported beam, and it is telling you that there is a concentrated load applied at the midpoint. So this is your concentrated load applied at the midpoint. This is your length L by 2. This is your length L by 2. Now, in this case, it is telling you that theta AP is the slope at support A. Okay, so now we will make the deflection profile of this beam. So the deflection profile of this beam looks like this. Okay, and in this case, this angle, it is telling you to be theta AP. Fine, this is what he has told you in the first line. Now he is telling you that now if the load of same value is equally distributed over the length, that means your P is distributed over whole length. Let's say we will tell it to be W. Then we get the slope at support at as theta u. Then find the relationship between theta p, theta ap, and theta au. So we will make another beam. In this, it is also simply supported, but in this case, now the load is not concentrated. Now the load becomes uniformly distributed load. Fine. So let me draw uniformly distributed load. So suppose this is our uniformly distributed load, and we have already mentioned that if we have P as a concentrated load, if we divide it by L, we will get as W load per meter. Okay, so this is also, we have theta A and theta B, and in this case he is telling you that the deflection profile has slope theta AU at support A. Now we have to find, so to find, in this case you have to find the relationship between theta AP and theta AU. Okay, so if you know all the standard results, then you can directly solve. Let me tell you first the standard results, but we will not solve the first problem using standard results. I will tell you the whole procedure, and from this problem, we will after this problem we will utilize all the standard results. So for this problem, I will tell you that how we can determine the values. So if we talk about the standard results, so for case 1, so let me write, suppose this is case 1 and this is your case 2. So for case 1, your theta AP as per standard result is PL square upon 16 AI, and for case 2, your theta AU is equal to WL cube upon 24 EI. If you want to check whether these results are correct or not, I have provided the table in the previous slides. You can check in that also. Okay, let me solve them for you for this current question, that how I got this theta AP. Okay, I will copy this diagram in the next slide. Okay. So I have copied this diagram in this slide. So in this case, if you find the bending moment diagram, how it will look like. So if you have to draw the bending moment diagram, okay, how you will draw this. So suppose these are the points where you have to determine the bending moments, and if you draw the bending moment profile for this case, it will look like a triangle, isosceles triangle. Fine. So in this case, the maximum value will come as PL by 4. Fine. If anybody wants to know how this PL by 4 came, so moment at L by 2, how we will calculate? If this is load P, what will be the reaction here? This will be P by 2, and this will also be P by 2. So your moment at HH section will come out to be P by 2 into L by 2, because at center it will give you PL by 4. Now you have determined the bending moment diagram. So now change this bending moment diagram into bending moment divided by EI diagram. Okay, so suppose now I am extending this. I will make this diagram to be M by EI diagram. Fine. So how it will look like? So this will again be a triangle fine, but now the value of the peak will be PL upon 4 EI. Now this is your M upon EI diagram. Okay, so as per first theorem of moment area method, your theta AP will be equal to area of bending moment diagram between A and P, between A and P divided by EI. So what area will come between A and P? So let me mark this. So suppose this area will come under A and P. So in this case, your area will be equal to 1 by 2 into what will be the total height is PL upon 4 EI, or you will write PL by 4 because EI we have already taken, into what is the base length is L by 2 divided by EI. So that means your theta AP is coming out equal to PL square upon 16 EI. Okay, so this is how we will solve the problem and determine the slope at that one particular point. So now let's solve for second case. So for case 2, so suppose for case 2 also, you have the result WL cube upon 24 EI. If we try to find out how it came, so let me write. So we will again draw the bending moment diagram for these profiles. Okay, so in this case, how the bending moment will look like? It will look like a parabola. This we already have covered, that why parabola will come for simply for uniformly distributed load, and why isosceles triangle is there for concentrated load. So in this, the peak value, the maximum value in this case will be, suppose this is maximum value, it will be WL square upon 8. So this is your bending moment diagram. Now if I convert it into M upon EI diagram, then how it will look like? Again, it will be a bending moment diagram. Now the maximum value will be WL square upon 8 EI. Now if we want to calculate theta AU, then what you will do? You will find the area of bending moment diagram. Okay, since I will find it between A and P, so let's say this point is P, or U, I will write U. Okay, so in this area of bending moment diagram between A and U divided by EI. Now this is your area that you have to calculate. So how you will calculate this area? This area will be equal to 2 by 3 into base, that will be L by 2, into height, that will be equal to WL square upon 8, and this will be divided by EI. If you solve this, you will get WL cube upon 24 EI. So now you know how to get the standard results. Okay, so now let's solve this problem. They are telling you to determine the relationship between theta A, theta AP, and theta AU. So relationship between theta AP and theta AU. So how you will determine? So from first case, we have determined theta AP to be equal to PL square upon 16 EI. Your theta AU for the second case, just now we have calculated it as WL cube upon 24 EI. So let's divide both of them. What you will get, we will see now. So theta AP upon theta AU will be equal to PL square divided by 16 EI into 24 upon EI divided by WL cube. This will give you 6 upon 4 P upon W into L. Fine. That means it will be equal to 3 by 2 because P is equal to WL. This will give you the ratio of theta AP to theta AU equal to 1.5. Fine. So we have solved the first problem. So second problem. So now let's move to next problem. So in the next question, it is telling you for a cantilever beam of length 2 meter, a downward load P and an anti-clockwise moment M is applied at the free end B. So first draw this. So we will first make a cantilever beam. So this is of length 2 meter, over which a point load is applied at the free end. So this is our point load, and anti-clockwise moment is applied at the free end. So now you have two loads here. You have point load as well as the moment. So what we will use? We will use principle of superposition. So let's first write what the questions want to ask you. So now to get zero deflection at the point B, you have to find the correct relationship between P and M. Okay, we have to find the relationship between P and M in such a way that your deflection at end B, so suppose this is AB, so your delta B with respect to A should be equal to 0. This is given. Okay, so this is given. What we have to find? We have to find relation between P and M. So if we see from here, we can divide this whole beam into two parts. Like we can do that whatever deflection we are getting through a point load plus whatever deflection we are getting due to moment alone. That means we are utilizing principle of superposition. Okay, so by this, if you can see, the beam will move like this. Okay, and you will get here one deflection, and due to this, beam will move like this, and this will be your another deflection. Okay, if we can add both the deflections, we will get to know, and we will make it to 0. We will find the relationship between P and M. Okay, so let's mark them. So suppose this is your first case and this is your second case. So for case 1, using standard results, what will be the deflection? So if I write theta at delta at B due to point load P, that will be equal to PL cube upon 3EI. And for case 2, if you have to find the deflection at B due to moment M, that will be equal to ML square upon 2EI. Fine. Now, what is given to you? Given is delta at B with respect to A is equal to 0. That means, let me write this also. Suppose I am taking this as positive and this will be negative. Okay, because one is in upward direction and another is downward direction. That means your delta BP plus delta BM should be equal to 0. Now substitute the value of delta BP. You will get PL cube upon 3EI minus ML square upon 2EI to be equal to 0. This will give you PL upon 3 to be equal to M upon 2. Fine. Let's continue in this slide only. This will give you P equal to 3 by 2 ml. Now substitute the value of L. You will get 3 by 2 into m by 2. That means P will be equal to 3 by 4 m. Fine. Now you have determined the relationship between P and M when you have one standard result given to you that the deflection at B with respect to A is 0. Fine. Now let's solve another problem. So next question tells you, if the same beam that you have utilized in the previous torsion, in that case, if you have to get the slope also at the free end equal to 0, now you have to find the correct relationship. Okay, so suppose this same beam is there. So let me copy this beam. Okay, if same beam is there and you have to determine the slope at end A and B, so I will copy this also. Okay, so suppose these are your profiles, and in this case your slope at due to at case 1 is coming out to be theta BP. Let me write it properly. So suppose here theta is theta BP, and here the slope is theta BM. Now we can again use the principle of superposition to determine the relationship between P and M. So in this case, what is given? So given is theta at B is equal to 0. Fine. Now what you have to find? You have to find the relationship between P and M when slope at the free end is 0. So how you will do? So your theta at BA will be 0. That means your theta BP plus theta BM is equal to 0. So for first case, using standard results, if we try to find theta BP, so your theta BP will be equal to PL square divided by 2EI. And for case 2, your theta BM will be equal to ML upon EI. Fine till this point. So now if you want to find the relationship between them, how you will find? We will take PL square upon 2EI minus ML upon EI to be equal to 0. If we solve further, what we will get? We will get PL upon 2 to be equal to M. That means P will be equal to 2M upon L, and it will give us, if we substitute the value of L, it will give us P equal to M. Fine. So this is how you will utilize the principle of superposition in case you have the standard results available with you. Now let's solve other problems. So next problem is telling you have to determine the slope at point B. So you have to find the value of slope at point B using the given load conditions. So in this case, you are provided with a simply supported beam subjected to uniformly distributed load over the whole length of the beam. So if you draw the bending moment diagram, so what you will get? So if you draw the bending moment diagram, it will be parabolic with maximum value coming at center, and this value will be equal to WL square upon 8. Fine. And if I try to find this value, it will come out as 4 into 4 divided by 8. That will be equal to 2. Now, if you draw the M upon EI diagram, it will look like this, having the maximum value as 2 upon EI. Okay. Now this is your M upon EI diagram. Fine. Now you have to determine the slope at point B. Okay. So how I can find out? I can find out by taking the relative slope. So suppose this is point P. Okay. So I will find the theta B with respect to P. So that means that will be equal to theta b minus theta p. Since slope at point P is equal to 0, because at center there is no slope, that means you have to determine this area, that means area of bending moment diagram between B and P and divide them by EI. Okay, so that will be equal to 2 by 3. What is the value of your maximum? Is 2 upon EI. And what is your value of the length? So total is 2, so that means 1 divided by, sorry, only 2 divided by EI. It will give you 4 upon 3 EI. Fine. So this implies your slope at B will be equal to 4 upon 3 EI. Fine. Let's move to another problem. So your next problem is you have a cantilever beam which is subjected to moment at free end in the clockwise direction. So in this case, you have to determine slope at point B and deflection at point C. Okay, so let's start with finding the deflection. Okay, so in this, how the beam will deflect? The beam will deflect like this. Fine. And in this case, your delta at B, that means this will be your delta BA. Okay, and this would be your delta CA. Fine. So we will calculate delta CA. How we will calculate? We will first make the bending moment diagram for this case. So in this case, you can see a constant moment is applied. So if constant moment is applied, you can see the bending moment will be like this, and it will be equal to a value of 50 kilonewton meter. This is your bending moment diagram. Now convert this into M upon EI diagram. So if we convert it into M upon EI diagram, how it will look like? Same as the bending moment diagram, but now the value will be 50 upon EI with negative symbol. Okay, so this will be your M upon EI diagram. Now to find the deflection at point C, what you will do, you will take the moment of the area. So which area you will take? So you have to take this area. Moment of this area will give you the deflection at point C. So that means your delta at CA will be equal to delta C minus delta A. Since delta at A is equal to 0, it will give you delta C, which will be equal to moment of area between A and C divided by EI. So first we will determine the area between A and C. So between A and C, you have area equal to 50 into 4, and if you have to determine the moment, the moment will be equal to 4 by 2, because it will be half of the rectangular section divided by EI. That means 80 into 50, it will be equal to 400 upon EI. Okay, since this value is negative, this will also be negative. Now substitute the value of EI as it is given to you in the question. That will be equal to 2 GPa, 200 GPa, and 100 into 10 power 6 mm to the power of 4. If you write it, it will be 2 into 10 power 13, and this will give you the result as minus 20 mm. So your deflection at point C is equal to 20 mm. Fine. Now you have to find the slope at point B. So if you have to find the slope at point B, so your theta at point B with respect to A will be equal to theta B minus theta A. Now this theta A will be equal to 0. That means it will be equal to area of bending moment diagram between B and A divided by EI. If I write the area, it will be equal to minus 50 into total length is 6 divided by EI. It will be equal to minus 300 upon EI. And if you substitute the value of EI, it will be equal to minus 300 divided by 2 into 10 power 13. Okay, and this value will be equal to minus 0.015 radians. Okay, so your slope at B is equal to minus 0.015 radians. Fine. So now we have found the slope as well as deflection at point B and point C respectively. Okay. Now next question is you have to find the deflection at point B. So in this case you have to find the deflection at point B. So how you will find? Again we will make the bending moment diagram at of the whole section. Okay, so if we draw the bending moment diagram of this whole section, and if we take, then we will take the moment of the area, it will give us the deflection at point B. So what will become? So in this case, the bending moment profile will look like this. Fine. So let me write, I will directly write as EI diagram. So in this case, your maximum moment will come out as 12 into 2, 24 divided by EI. Fine. That will be equal to 24 upon EI. How I calculated it as? Suppose At this point, till this point, moment at x is 0. If I further proceed, your moment at x will be equal to 12 into x. Fine. This is how moment will come now. Into x by 2. That will also come. So that will give you 12 x square upon 2 equal to 6x square. So if I write here, that will be equal to, how I will write in terms of this section. Here, if I write in terms of x, it will come out as 6 into 4. This will be my moment divided by EI. That will give me 24 upon EI. Okay, now I have to find the deflection at point A. So this is a quadratic curve. Okay, so if you have to determine the deflection, how you will determine? So let me write your delta at B with respect to A will be equal to delta B minus delta A. Now your delta A will be equal to 0. That means it will be equal to moment of area between B and A divided by EI. So first we will find the area of bending moment, area of the bending moment diagram, how it will look like. It will be equal to 1 by 3 into, how much is the base? Base value is 2. What will be the altitude? Is 24 upon EI. And if we have to find the distance, so first distance is up to 2 meter, it is 0. So 2 will also come. Plus, and for triangle, we will utilize 2 by 3. In this case, we will utilize 3 by 4. So 3 by 4 of the rest of the length, which is 2 divided by EI. This you can learn from solid mechanics also. Then how can you determine that moment, or you can say centroid of a quadratic curve or 3-degree curve. In that case is how you have to determine the value of the lever arm, or you can say the centroid. So that's why 3 by 4 come into picture here. So if you solve them, what you will get? So here you will get 16 upon EI plus 2, 4, 4, 3, 7. So this will be equal to, if I write it here, it will come out as, so this will be 4 plus 4 into 8, 8 and 6, 14 upon 4. That means it would be equal to 16 upon EI into 7 upon 2, that will be equal to 56 upon EI. Fine. So your deflection at point B will be equal to 56 upon EI. The calculation of determining the moment, or you can say the lever arm of the 2-degree curve, you have to know first. Then only you will be able to solve the problem. And also you have to know in what cases the profile is 2-degree and in what cases the profile is 3-degree. Then only you will be able to solve this. So next question is, you have to find the deflection at point C of the following beam. So in this case, you have a beam which is having different moduli, or you can say different modulus of inertia, different i's. Okay, so if you have different I values, in this case you have 2i, and in this case you have I, considering E to be same, like in this case E is also same. So how you will determine the bending moment diagram? So let's see this. So let's draw the bending moment profile. So you have a concentrated load at the free end of the cantilever beam. So in this case, the bending moment diagram will be linear. So, okay, so let's draw this linear diagram. How it will look like, we will see. Okay, so in this case, if you draw the bending moment diagram, you can see that till 2, it is 50 kilonewton. Okay, then just to the left of B, you can say the bending moment profile reduces to half, and then again it increases to certain value. Okay, and then it is okay. Now if we try to determine the values, how it will look like. So in this case, it will come out as 25 into 2, that is 50 upon EI, and suddenly the value of I decreases to half. So that means the value here will come out as 25 upon EI. Then from this, the value increases, and what it will come as 25 into 5 as 125, and 125 divided by 2 EI. Fine. You have understand how the value came. So up to this level, it is 25 upon EI. Now I have to determine the deflection at point C. So what I will do, I will divide the whole beam into 3 sections. So let's say this is section 1, this is section 2, and this is section 3. Why I am dividing? Because I have to determine the moment of different areas. So if I divide the diagram, then it will be easy for me to determine the moments. Okay, so your deflection at point C with respect to A will be equal to deflection at point C minus deflection at point A. Since deflection at point A is equal to 0, then it will be equal to moment of area between A and C divided by EI. So first we will find moment of area. So I will find moment 1, moment 2, moment 3 of 3 section divided by EI. Let me determine first moment. So your M1 will come out as 1 by 2. What will be the total height? 50 upon EI. Base length is 2. And what will be the distance? It will come out as 2 by 3 of 2. Fine. If you solve this, you will get it as 200 upon 3 EI. Now I will determine second section moment. So second is a rectangle. No, second is also a triangle. It is 1 by 2. Altitude is in this case will be 125 upon 2 EI minus 50 upon 2 EI, 50 upon minus 25 upon EI. Okay. Now you have to find the moment of this. It will be equal to 2 plus 2 by 3 of 2. Fine. Till this point. If you try to solve this, you will get it as, it would be 25 into 50, and that will be 75 upon 2 EI. That will be 75 upon 4 EI into 3 into 2, 6 plus 4, 10. 10 upon 3. That will be 15 into, that will be 525 upon 2 EI. Fine. Now third moment. So third moment, if we calculate how it will look like. So your third moment, since it is also a triangle, it will be 1 by 2 into, no, this is rectangle. So then in this case, it would be 25 upon EI into, what will that length? Length is 3 meter. And what will be the lever arm? That will be equal to 2 plus 3 by 2. If you solve this, you will get the value as 225 upon EI. Okay. So now let's make the moment for all these cases. So then in this case, if we add all the three moments, so your delta C will be equal to M1 plus M2 plus M3. That will be equal to 1 upon EI. EI I am taking it out into 200 upon 3 plus 525 upon 2 plus 225. That will be equal to 3325 upon 6 EI. If you substitute the value of EI here, that will be equal to 3325 divided by 6 into E is 250 GPa. So 250 into 10 power 3 and 200 mm square, mm to power 4. Okay, so this will give you the value of theta, delta C to be equal to 11.08 mm. Fine. So you have to break the problem into three parts, then it will be easy to you to determine the value of moments. Now let's solve one more problem. In this, it is given to you that you have to determine the deflection at point B. Now, if you have to find the deflection at point B, since this is a combination of uniformly distributed load and uniformly varying load, then how it will look like? So this beam, you can divide it into two parts. So if you divide it into two parts, your first part will be a uniformly distributed beam. Fine. So your first part will be uniformly distributed beam. And in that case, if you find the moment at any section, how it will look like. Suppose it is W. So W into H at H by 2, that will be equal to WH square upon 2. So that means your degree of curve will be quadratic. But in case of uniformly varying load, you can see if this is your uniformly varying load, in this case, if you try to find the moment at HH, it will be equal to 1 by 2 into W into, since if total is W, then at any distance H, suppose this is my maximum value is W. So at any section H, it would be equal to WH by L. So that means WH by L acting at a distance of H by 3. Okay. Into length is also will be there. That will be equal to H. And it will be equal to W H cube upon 6EL. That means your moment, bending moment distribution for uniformly varying load will be a 3-degree curve. Okay, so now let's draw the bending moment diagram for this case, how it will look like. So in this case, if you try to determine the bending moment diagram, we will divide it into two parts. So your first will be a 2-degree curve like this. Again, I will make it with this line. Fine. And in this case, the value will come out as, if we put H equal to 5, that will come out as W is 5 into 5 square upon, how much I have written it, is 2. That means it will be equal to 125 upon 2 EI. This is for UDL, 2nd-degree curve. Okay. And now for uniformly varying load, it will be a 3-degree curve. Correct? And in this case, the maximum value will come out as W H cube upon 6L. So if I write as W here, it is will be 10 minus 5, 5. H cube will be 5 cube divided by 6. L is how much? 5 into EI. That will be equal to 125 upon 6 EI. So this will be your 3rd-degree curve for uniformly varying load. Now we can combine the deflection by both these curves, and then we can determine the slope as well as the deflection at point B. So your slope at point B with respect to A will be equal to slope at B minus slope at A. Your slope at A is 0. That means it will be equal to area of bending moment diagram between A and B divided by EI. Now we can find out the area of both of them separately for both UDL and UVL. So that means area of UDL plus area of uniformly varying load divided by EI. So if I try to find the area of UDL, how it will look like? It will be 1 by 3 into 125 upon 3 EI, that is the height. And how much is the length? Length is 5. It will come out as this. It will come out as 625 upon 6 EI. And if I try to find the area of UVL, it will be equal to 1 by 4 into 125 divided by, in this case, it is 6 EI and total length is 5. And here it is coming out as minus 625 upon, here it is 2, no? Yeah, 2. 625 upon 24 EI. Okay, so your theta B will be equal to minus 625 upon 6 EI minus 625 upon 24 EI, and that will give you the total value as minus 3125 divided by 24 EI. Fine. Now in this case you have to find the deflection also at point B. So if you have to find the deflection, so your deflection at point B with respect to A will be equal to deflection at B minus deflection of A. Deflection at A will be equal to 0. That means it will be moment of bending moment diagram between A and B divided by EI. That will be equal to moment of bending moment diagram for UDL plus moment of bending moment diagram for UVL. So if I try to find it out, so your moment of bending moment diagram due to UDL, how it will look like? Area you have already know how to calculate, that will be 1 by 3 into minus 125 upon 2 EI into 5. This is your area. Now you have to take moment of this area. How you will take? This will be equal to, since you are taking from the point B, it will be equal to 3 by 4 of 5. Okay, and this will give you the value as minus 3125 divided by 8 EI. Similarly for UVL, if you try to find out, it will be equal to first area 1 by 4 into 125 divided by 6 EI into length and the moment, it will come out as 4 by 5 of 5 and it will be equal to minus 625 upon 6EI. If you add both area of moment of this area of bending moment diagram, then you will get the deflection at point B. So your deflection at point B will be equal to minus 3125 divided by 8EI plus minus 625 divided by 6EI, and that will be equal to minus 11875 divided by 24 EI. Okay, so this is how you will solve the problems related to calculation of deflection and slope. Now one last problem. In this, you have to find the deflection of uniformly varying load at point B. Now in this case, you can see the problem is reversed. Earlier, your maximum uniformly varying load is coming out at point A. Now in this case, the maximum uniformly varying load is coming out at point B. So in this case, if you have to determine the moment at any particular section, so suppose in this case, I have to find the moment at this. So first, start calculate this value of reactions in this. So suppose this is your VA and this is your MA. Let me draw with red. It will be easy to understand you. Suppose this is your VA and here you will get moment also as MA. So your VA will be equal to 1 by 2 into 4 into 36. That will be equal to 72 kilonewton. And if you calculate your MA, how it will look like? It will be 1 by 2 into 4 into 36 into 2 by 3 of 4. That will be 72 into 8 upon 3, and that will give you the value as 192 kilonewton meter. Now, if at any section XX, you have to find the moment, how you will determine? So moment at XX will be equal to plotwise moment should be taken as positive. That means VA into H. Let's say this is distance at as H. VA into H minus MA and minus of 1 by 2 into 36 into H upon L. L is 4. Multiply by the distance. That will be H upon 3. Fine. That will be equal to VA into H minus MA and minus 3 by 2 H square. So this you got the moment at any particular section. Okay, so that means if we combine all these three moments, we will get to know the value of moment at that particular section. So let's draw. So if I take this as 1, this as 2, and this as 3, so let's draw 3 bending moment diagrams, how it will look like. So since it is VA into H, it will be a linear profile. This would be a linear profile. Fine. So this is for VA, and its value will come out as 288 upon EI. How it came as? VA is 72, total length is 4 divided by EI. So this is due to VA. Now we will draw due to moment M. So that will be negative moment So this will be a negative moment, and this will be due to MA. It will come out as MA. So MA we have already calculated as 192 upon EI. Third, it will be due to the H that is provided. Okay, and in this case that will be a cubic. So how we will draw? So we have to draw a cubic profile. And that will also be a negative, and it will come out as, if we write here, that is coming out as 3 by 2 into H is 4 cube, and it is 96 upon EI. That means we have to determine the moment of area of all these curves, then we will be able to determine the deflection at point B. So deflection at point B, so let's say this is 1, this is 2, this is 3. So your deflection at point B with respect to A will be equal to deflection of B minus deflection of A. Since deflection at A is equal to 0, this will give you deflection at B as moment of area between A and B divided by EI. That will be equal to moment 1 plus moment 2 plus moment 3. So your moment 1 is due to shear, that is value of shear VA, and it will be equal to 1 by 2 into 288 upon EI. What is the total length? Total length is 4. So since you are considering the moment from B, that will be 1 by 3 of 4, and that will be equal to 768 upon EI. Now moment 2 will come out due to constant moment that is applied, and it will be area of the bending moment will be 192 upon EI into what is the length? 4. Now multiply by the distance, that will be 4 by 2. If you write, it will come out as minus 1536 divided by EI. So your third moment will be due to the additional term that comes into picture, and that will be equal to, since that will be a third degree curve, and its area will come out as 1 by 4 into minus 196 upon EI into length 4, and now we have to take the moment of this area. That will come out as 1 by 5 into 4. and it will be equal to minus 76.8 upon EI. Now adding all the three moments will give you the deflection at point B. So your deflection at point B will be equal to 1 upon EI into 768 minus 1536 minus 76.8, and this will give you the deflection at B to be equal to 844.8 divided by EI. So by this, we have covered all the problems that you are expected to solve for this current week. Anyone having any doubt in this session? I will wait for 1 minute. So in this session, what we have done, we have tried to determine the value of slope and deflection at a point in beams. How we have determined? Using moment area method. So what is moment area method? So moment area method is based upon two theorems. So what does these theorems tells you? So first theorem tells you that if you have to determine the slope at one point, it will be equal to the bending moment, the area of the bending moment diagram between those 2 points divided by EI. Next is if you have to determine the slope at another point, it will be equal to moment of the bending moment diagram area that you have calculated divided by EI. So by this, you can calculate the slope and deflection for different points in beams as well as in frames. So what you will cover in the next week? So your next week will take into account the calculation of bending moment, deflection as well as slope for beams and columns using conjugate beam method and virtual vert method. So by this, we will cover our statically determinate structure due to static loads. Okay, so let's wrap up this session. If anyone has any doubts, you can post in discussion forum also. Okay, so let's meet on next Saturday. Till then, enjoy your weekend and have a nice day. Thank you, everyone.